Alright, hopefully you're ready for the second example because this is going to be a little bit harder to solve. But if you do this one, if you understand this one, oh boy, you're ready to solve integrals using partial fractions. So let's begin. As always, we have our three steps, and obviously I'm going to do partial fraction expansion because if I assuming that I already asked myself, can I use u sub, which in this case is not going to work. And so since I know that this is obviously a rational function, it's a big rational function, the natural question to ask after the u sub question is to ask myself is if I can use partial fractions to simplify the process, which is what I'm going to try now. With that being said, I'll try the three steps. Step one being, is this proper or improper? We can see a degree 4 in the numerator, which is higher than the degree of the numerator. Therefore, it is proper. Okay, so we can move on to step 2, which is to verify the denominator. Can we factor out that denominator? So I'm going to write down the numerator over here. Can we factor out x to the fourth plus 4x squared plus 3? And the answer is yes. I'm going to take the x to the fourth and look at it as x squared squared. Okay, x squared squared. And with that, I'm going to have two parentheses with an x squared on each side. Plus plus gives me plus plus. And then 1 times 3 is 3. 1 plus 3 is 4. So 1 and 3 are my values. Okay? Then I rewrite the numerator, which stays the same. And now x squared plus 1 and x squared plus 3 are irreducible quadratics. There's no way I can simplify them any further using real numbers. So I'm going to split them into two new fractions. One with x squared plus 1 and another one with an x squared plus 3. Since they're irreducible quadratics, according to the table we looked in the previous videos, we need a linear term on the numerators. And that's why I'll put an ax plus b and then a cx plus d. And now we have four variables we have to discover. So I'll do the smiley face here in the bottom, and I'll have ax plus b, x squared plus 3, plus, and then cx plus d, all times x squared plus 1. The denominator is just, these two being multiplied. I don't really have to write them down. Ultimately, they'll cancel out with the first expression. We have expression 1, 2, and 3. Now comparing expressions 1 and 3, I got that x cubed minus 2x squared plus 2x minus 5. And canceling the denominators, obviously simplifying it. Then I have the right-hand side, which is all of this. And what I'm going to do is just expand everything out, okay? So I'm going to get ax cubed from here plus 3ax plus bx squared plus 3b. And if we continue, I got a cx cubed plus cx plus dx squared plus d. I could attempt to group the a's and the b's and the c's and the d's, and maybe I could solve it. However, I'm going to go with the approach of treating this as a system of equations. There's four unknowns, a, b, c, and d. So I'm going to create a system of four equations over here. And the way I do that is I treat every set of powers individually. So I start with the x cubes, which are the highest powers over here. I have three terms. I can get rid of the x cubes in advance because I know they'll cancel out on both sides. And I have a 1 on the left-hand side, and the other side I have a plus c. For our second equation, I'm going to look at x squares. I have 3 once again, which give me minus 2 equals b plus d. And if I continue, I can look at x to the first power. There's 1, 2, 3 terms as well, which can be written as 2 equals 3a plus C, and finally for the constants, I have 1, 2, and 3 minus 5 equals 3b plus d. Okay, so I have a system of 4 equations and 4 unknowns, which means that I can find the solutions for each and every unknown. You can solve this using substitution or back substitution, I think it's also called. Another way, just for you to know if in case you're interested, another way you can solve this, which could be more convenient for cases like this where we have, well, a lot of unknowns and a lot of equations, we can use a matrix. So we can create a 4 by 5 matrix, and in this case, I'm going to show you how to create it. So there's 1A, no B's, 1C, 1D, and that is equal to 1. For the second equation, I have 0 A's, 1 B, 0 C's, 1 D, and that equals minus 2. For the third equation, I have 3 A's, 0 B's, 1 C, no D, equals 2. And finally, I have 0 A's, 3 B's, 0 C's, 1 D, equaling minus 5. And I close the bracket, and that is my 4 by 5 matrix. And I'm not going to solve it step by step here, neither of the two, but this approach is done or solved using substitution or backward substitution, and the matrix can be solved with the two basic techniques, which are the Gauss-Jordan elimination method, or you could do it using matrix inversion. Whatever method you choose, verify the answers that I'll give you here. I've done this, and it gives me that A is 1/2, B is minus 3/2, C is 1/2, it's positive, 1/2, and D is minus 1/2. So these are my 4 solutions, and I'm going to go ahead and plug them in my new integral. Okay, let's continue here. Okay, so this big integral can be rewritten as the integral of ax plus b. So a is 1/2 and b is minus 3/2 over x squared plus 1, and then the other term was x squared plus 3. C was 1/2, which gives me 1/2 x, and d was minus 1/2. All right, so this is the big new integral I need to solve. And now I ask myself once again, can I solve this either directly or with u substitution? And the answer is actually yes, but we do need to play around with this a little bit. And so a lot of the times this is going to happen. You just need to be a little bit strategic about this. And in here, notice that I can factor out a 1/2 for each fraction. So I'm going to do that. And another thing I'll do is split this into 2 new integrals, just to simplify things. Okay, so I'll factor 1/2 for the first integral, and I'll be left up with x minus 3. Okay, the bottom is the same, and our second integral, I'll factor out the 1/2 as well, and I'll be left up with x minus 1 in the numerator, x squared plus 3 on the denominator. Okay, so ask yourself again, can I solve this using u sub or direct substitution? The answer is yes, but what I'll do, this is just my preference, is I'll split each integral into 2 more integrals. So I'll have 4 integrals in the end. So 1/2, and I'll split them, so I'll have an x, and now there's a 3, a minus 3, okay? Multiplied by 1/2, I'll get minus 3/2, just 1 over x squared plus 1 dx. Moving on to the second one, I'll have 1/2. I'll leave the x, and then there's a minus 1. So minus 1 times 1/2 is minus 1/2. Integral of 1 over x squared plus 3 dx. And now I ask myself again, can I solve this directly or with u sub? And finally, the answer is yes. So if we take a look at each one individually, for integral number 1, I can say that u is equal to x squared plus 1, making du be 2x dx, which means that du over 2 is x dx. So I can take this and I can write du over 2. So I'm going to multiply this 2 by another 2. And this is just going to be u. So I'll have the integral of 1 over u du multiplied by a fourth, basically. And it's very easy. For the second integral, the integral of this integrand in particular is basically inverse tangent. There's going to be inverse tangent. Actually, you just have to multiply it by minus 3/2. The third one is going to be very similar to the first one. I'll use u sub once again. Say x squared equals x squared plus 3, equals u. And the u has to be 2x dx once again, and the u over 2 is x dx. So I use that once again to put my du. This is u, and I have to multiply this 2 by another 2. So I'll get a positive 1/4 of integral of 1 over u du. And finally, integral number 4 is similar to integral number 2. And this, believe it or not, is actually also inverse tangent. You just have to remember the general forms of inverse tangent and its antiderivative. So an inverse tangent was 1 over x squared plus a squared, which in this case a would be the square root of 3, right? And the antiderivative of that is 1 over that constant, 1 over a, times inverse tangent of x over a. Okay, so taking that as a reference, I have a minus half, and I have to multiply that by 1 over a, which is going to be 1 over root 3. And now inverse tangent of x over, again, root 3. And I'm basically done. I just have to solve integrals 1 and 3, and I'll be good to go. So finally, this is going to be, all of this is going to be equal to the first integral, so 1/4 natural log absolute value x squared plus 1, and then plus 1/4. I'm going to take the third integral to make it a little bit more consistent. Natural log absolute value x squared plus 3 minus 3/2, that's the second integral, inverse tangent x, and then the last integral is going to be minus 1 over 2 square root of 3 inverse tangent of x over square root of 3 plus c. So we're basically done. A couple things to consider is taking a look at x squared plus 1. That's always going to be positive no matter what x input you put. Same thing is going to be for x squared plus 3. Okay, and I know that because when you square something, it's always going to give out a positive number, so there's no way of the expression being less than 0. And that basically means we can eliminate these absolute value bars. You can do that. Technically, you have to, but sometimes people leave it, and sometimes, depending on the professor, that's fine. But I always like to remove them if applicable. And another little detail is for the roots. So apparently mathematicians hate having roots on the denominators. So what they would do is, in this case, multiply by root 3, the top and bottom. So then this can be rewritten as square root of 3 over 3 times 2, which is 6. And then this one, same thing, would look like inverse tangent of root 3 over 3 times x. Personally, as an engineer, I don't care. So I just leave it as is right now, and I'm cool with it. Looks cool, so. Alright, so if you've made it through this, I have one final example. If you're out for it, take a look at the next video. I'll see you there.